right, so it's recording now. So what am I gonna do? I'm gonna put a noble metal into the nitric acid, watch it react. Here we go. We got an easy source of noble metals right here, and plunk. Is the copper gonna react with the nitric acid? It is, pretty quickly. Well, it didn't do anything with the hydrochloric acid. What's happening to it? It's generating, they call that evolving a gas. That's a good sign of a chemical reaction, producing a gas. What? Okay, that's a very good question. Well, first of all, what color is that gas? Brownish orange. Is that a good color to have in the sky?
No.
This is the color of a lot of pollutants that we get in our sky. I'm only making a few grams of it right here. If it's a factory, a lot of factories churn this out by the ton. Could you come back a little later because we're doing a demo? Sorry. Then a lot of factories churn this out by the ton. And sometimes if you look at the sky, and if the sky is brown, and it's not because of the dust from the Santa Ana winds, then this is what is in the sky. A lot of this. To make the whole sky brown, imagine. It's a lot more than a few grams of it. These are called oxides of nitrogen. There's actually several of them. We'll talk about later. There's 3 different ones. And they're all combinations of nitrogen and oxygen, which is funny because nitrogen is clear and oxygen is clear. You're seeing right through it, look. But oxides of nitrogen, they all tend to be brown or kind of brownish orange. So that's a pretty good reaction, and that's been going for a few minutes. And I've been waiting this whole time for somebody to interrupt me, but nobody's interrupted me yet. I think somebody almost did. Oh yeah, one other thing you might notice, it's turning kind of green. That's because a lot of compounds of copper are blue or green, kind of aqua colored. But that's not what I was hoping someone would say. Oh, it's too bad I'm recording this. The sound is good. What's the main thing that I'm overlooking? Come on. Think of the isotopes of Pennium lab. It smells, that's true. It doesn't smell good.
The amount of copper in the penny.
The amount of copper in the penny. How much copper was in that 2015 penny? That was a 2.4%. It's zinc, yes. So that was what we call a psych, kind of like in bingo. That was not the real noble metal. But we are going to really do it, so watch carefully. What do I need? What penny do I need if I want it to be made of copper? What year?
1948.
Okay, that would work, but anything before what? What was the year they changed?
1940. 2000.
Well, they changed in 1982.
1990.
So let me see. Let me get another beaker with a little bit of nitric. A little bit of nitric. About 15 milliliters, about the same amount. And this time, let's find an older penny. Oh look, so luckily I have some underneath. Oh yeah. See, these were zinc pennies. These are the copper pennies. Oh, I must have thought about this. 1974, there we go. 1974 pennies were about 95% copper. So, let's see how copper reacts. Now notice, that shouldn't have been a surprise to you what just happened. Although I expected you guys to remember what it was made of zinc. Because look where zinc is.
Oh God.
Zinc, of course, is going to react with any acid, even hydrochloric. So that shouldn't be a surprise. But let's see if we can really get, actually, do you know what I'm going to do before this? I'm going to fish out what's left of that little penny in there. I'm going to fish out what's left of it so that we can pass it around later once I've washed it before it's gone. Because there's not much left of that little penny. So I'll wash it off and I'll take it around and show you at your lab station later. That was the zinc penny. Here is the real copper penny. This one is from 1974. It's 95% copper. So this will be the real debasing of the noble metal. Drop it in. So compare the 2 reactions. Is it the same as the zinc? Please unhand it, or unhand that. Is it the same as the zinc? Kind of, but is it as fast as the zinc?
No.
Definitely not as fast. Is it changing the color like the zinc did? Yes, but is the color the same? Well, let's see. Let's see if it winds up the same color. Is it producing that orangish brown gas?
Yeah.
Yes, so the same kind of product, oxides of nitrogen.
That looks red.
And now that I've taken the first penny out of there, I thought we would try something new, something I've never tried before. What's that country north of us? If you go far enough north, like Oregon, Washington. What's that country up there? Oh, it's La Cañada. Up in La Cañada, they have a penny too. I wonder what they make their penny out of. Do you think you're gonna be able to tell what their penny is made of? I haven't even researched this, so I'm not even sure myself what Canada makes their pennies out of, but we should be able to tell by the speed of the reaction. So this is something I want you to add to your lab report. By the way, we didn't do this in any other periods. They're gonna just see this video for it. But let's see what the Canadian penny, which has a queen on it. Well, I'm an anti-monarchist, so this is fine for me. Let's plop it in. This is still nitric acid, by the way. Even though it reacted with the zinc, there's still enough nitric in there. Let's not worry about that issue. Let's plop it in. So what would you guess? Looking at that, don't say it out loud because this is a video. I gotta show other periods. I'll have to turn the sound down. Don't say it, but think it. I wonder which metal makes up most of a Canadian penny. Don't say it. And then this will be something you can add to your lab report. I've never done that before, but I can tell right away. I know right now. I don't need to look it up. You probably don't need to look it up either. If I were to leave it in there for just another couple minutes, there wouldn't even be a penny left. So I'm gonna fish it out while it's still there, if I can get it, if it is still there. And then, I can't see it.
It's gone.
No, it's in there somewhere. I'll get it, because it's still reacting. The reaction would die down if it was that. Oh, there it is. There it is, come on. Got it. Okay, so, yes, it is hot. Good point. That leads us to endothermic, exothermic. I was gonna talk about that tomorrow. That's a very good observation. So I'm putting this penny in here. Right now it's covered in nitric acid, but I'm gonna rinse it off thoroughly before I take it around. You won't get any nitric acid on you, and you'll see what has happened to these pennies. And we are going to now do the nitric acid, super nasty acid in this bottle here. Does things no other acid will. It's a strong oxidizer. Okay, we're gonna react it with the zinc penny, which we've already seen happen. The zinc penny, you see what happens to the zinc penny, we know that. The copper penny, okay, this is a 1983 penny, this is a 1973 penny, okay. We know what happens to the copper too. It's a noble metal. Look up here, the noble metals, but we got it debased. Now we're gonna see what happens with the 1943 penny, kind of just for fun. We should know what's gonna happen with that, because a 1943 penny is made of steel, like Superman, and steel is iron, which on the activity series, look, is right, I don't know if you can see that down here, it's just below zinc, so that's kind of what we'd expect, but wait, it has carbon in it. Interesting that steel is not even completely metal. Steel actually contains non-metal. Interesting. Sometimes 2%, okay, carbon to reinforce the steel. And just to make things interesting, we're going to actually react a little bit of silver. It probably won't focus that close. A little bit of silver, and just see if that will react. Another noble metal, even more noble, let's say, than copper, even lower than copper on the activity series. So that'll be the other thing. I'll try to put them in at about the same time so we can have a fair fight once again, like we did last time. And I'm gonna plop them one after the other. Zinc, okay, 1983. Okay, steel, 1943. Copper, 1973. And bye-bye earring. Okay, silver, argentum, like little Argentina. Let's see how these go. So look at the reaction rates. It's interesting that it might not have been what we predicted. what you might have written in your lab report already. Okay, obviously, once again, the clear winner, producing all these oxides of nitrogen. Okay, all of these oxides of nitrogen, which I took off the board. Okay, one that I didn't have last time, I was going to bring up. One that I did not bring out last time, we already mentioned that nitric oxide is produced. Well, nitric oxide, in the presence of regular atmospheric oxygen, often winds up producing some ozone. Okay, ozone is an allotrope of oxygen, O3. Okay, and ozone is different from regular oxygen. When I say oxygen, I mean this. Okay, ozone is O3. Okay, so we've already seen the zinc and copper react. Interesting that the 1943 penny is reacting less than we might have predicted. You might want to back away slightly. Okay, we don't want to be exposed to too much of these oxides of nitrogen. Okay, but let's keep it running and we'll see if we can get the steel to react, and we'll see if we can get the silver to react. Okay, another noble metal. This is the thing about experimentation, is it doesn't always match your prediction. So we're just gonna see what happens. That's so fun. Thank you for helping me. I'm just gonna keep watching it and see if there's any reaction.
Not doing anything, is it?
At this point, it's not. It might be tarnishing. I'll take a look at it. I'll fish it out. Looks like the silver is tarnishing. It's hard to get close with all these fumes. But I see some green in there. And I see a discoloration in the steel one. Yeah, but clearly not reacting at the rate we would have predicted based on iron on the activity series. Look where iron is. Okay, look where copper is, and yet the copper is reacting more. Another factor that we should consider is that the steel penny was the only penny ever made, only coin ever made that doesn't contain copper. Okay? And even the old penny did contain a little bit of zinc. It was kind of a bronze alloy. So maybe the zinc got the copper started, you could argue that. Okay, interesting that the other coins, the nickel, the dime, the quarter, are made mostly of copper, and people don't think they are, whereas the penny is made 97.5% out of zinc these days, and people still think it's made of copper. So it's almost the reverse of what you think. It now costs more to make a penny than a penny is worth. It costs around 2 cents to make a penny. So the government loses millions of dollars every year just making them. Okay, I'm gonna keep an eye on this. So obviously, clearly the reaction with the steel is very slow. The reaction with the silver is even slower, although there is a discoloration. So what I'll probably do is in a little bit, by the way, there goes the last of the zinc penny. The last little bits, those are fizzing around there. That's the last, boop, that was it. That was the end of the zinc penny. That was the 1983 penny. Okay, the copper penny isn't gonna last too much longer this time. I'm just gonna let it go to completion. Let it go bye-bye. And then we'll see how much reaction we get with the other two. So was that what you predicted with the 1943 penny? Is this what you expected? Maybe. And nitric acid, super nasty acid. Does things other acids don't. Okay, has the hydrogen ion, which makes acids, that's why hydrogen's on the activity series. These usually react with acid up here. Okay, but it also has the nitrate, the nitro group. That's found in most explosives. It's found in nitroglycerin. Okay, saltpeter. And it's found in ammonium nitrate that we used in the cold pack lab. We're getting down to the end of the copper penny. Notice how it's taking longer. That makes sense. Okay, see the bluish color, the greenish color? Copper compounds generally produce aqua blue or green colored compounds, even though copper itself, as you know, has that characteristic sort of orangish color. Copper compounds, on the other hand, are generally known to have a blue or green. We notice that in a lot of minerals that contain copper. Alright, so, got the tweezers. I'm gonna fish out what is left, most of it. Got a little woof, silver. And it's hard to stand above nitric acid. It's a nasty stuff. Okay. I'm gonna have to put my phone down to do this with 2 hands. Steel penny doesn't look any different, honestly. Pretty much as good as new. I'll take the mass to see if any's been lost. Still see everything, still read the small print. Looks just like it did originally. The silver earring does look damaged. I'll wash it off and I'll take the mass of it as well. All right, enough of being penny ante. Now I'm gonna nickel and dime you. Nickels and dimes, I wonder how they react. We've already seen pennies, we've seen the old penny, we've seen the new penny, made of zinc and copper. I forgot to show some periods about nitric acid, that it really is an acid. So let me just show you, universal indicator. If I put a few drops in, look at the one in the middle. That's pretty red. Right away, just a couple drops, pinkish at this point. That's red. Okay, that is a good acid. Plus, it's got the nitro groups to boot. Here goes the nickel. Okay, 5 cents, it says on there. That's useful to know. Here goes the dime. 1 dime, it says on there. That's not as useful. If you don't know what a dime is, you'll never figure out what that means. It doesn't say 10 on there. What? That's really useful for people from other countries. Plop it in. Okay. Wow, that's interesting. Nitric acid even reacts with universal indicator. Not a lot of things react with universal indicator. That's funny. And then you can tell by the color and the speed of the reaction what they're made of. You're probably guessing, which one does this look more like? Does that look more like what we saw with the old penny or the new penny? They both gave off brown gases, but the color was a little different and the speed of reaction was a little different. So does that look more like the copper penny or does that look more like the zinc penny? Interesting. Let me see if I can fish out, let me fish out the dime first. It's still reacting pretty strongly. Not gonna let it finish. There we go. There goes our little dime. There goes our little, where's our little nickel? Plug nickel. Gotta fish it out of there. It's gotta be in, there it is. We got the nickel. So what I'll do is, all right, I couldn't resist doing it. What about a quarter? Same thing, nitric acid, plop it in. What are quarters made of? You can probably tell by the reaction, the speed of the reaction, how quickly The oxides of nitrogen are given off here, what it's probably made of. We already saw the dime, that's when I fished out the nickel. We've seen several different pennies, even Canadian pennies. And you can probably guess that that's kind of like the nickel. That's kind of like the dime. So surprisingly, nickels, dimes, and quarters are made of the very material that most people think pennies are made out of, and yet pennies are not made out of it. How ironic. Let me fish it out. Wasn't in there as long, wasn't in there too long, but we'll see what difference that makes. In the cold pack lab, we will be examining an ionic compound. Well, this one happens to be an explosive ionic compound, but we're just using it for the fact that it is an ionic compound. Ammonium nitrate. Ammonium nitrate is made of 2 polyatomic ions, ammonium and nitrate. Water is capable of ripping them apart. When water rips them apart, water has some energy. When it rips them apart, water has less energy. We're going to record that on our thermometers, and we're going to decide if it's an endothermic or exothermic reaction or change. Okay. We're going to be measuring out 4 portions of the ammonium nitrate. We're going to be putting them in beakers. We usually put them in filter paper. I decided this time for visibility on film, it'd probably be better to put them into the beakers, but we typically do it on paper. And we're going to pour them into a not so big amount of water. You're going to see how much water it is. It's going to seem like a whole lot to go into a very little bit of water. Remember, we're only adding the water once, but we're adding ammonium nitrate 4 times. Okay, as the experiment goes on, we're going to be adding 10, and then another 10 gets you to 20, and then another 10 gets you to 30, and then another 10 gets you to 40. We're going to eventually add 40 grams, probably like about half of what's in there or more than half of what's in there of ammonium nitrate into a beaker with a cup inside it. Now the styrofoam cup is a little bit of an insulator. It slows down the transfer of energy to the outside world, except for on the top. So we're doing our experiment inside a styrofoam cup, and then the beaker is really just to stabilize it. I put a couple of cups in there just so it fits better. But it's really just one styrofoam cup that we're doing the experiment in. And we're going to try not to puncture it with our stirring rods when we're stirring. Okay, we're trying not to puncture that, and especially not with our pointy thermometer. So obviously the room temperature is around 24 degrees Celsius, 24.2. These thermometers are fairly accurate. So that'll probably be one of our higher temperatures on our graph when we graph it. And then we'll see, well, it's called cold pack. Okay, we'll see what happens to the temperature as we go on. We'll see what the most effective use of this material is. Now, by the way, this is the same chemical that is used in some cold packs. You put it inside a pack. The pack is separated with a little lining from the water, and then you smack the pack, and the water flows in, causes them to be ripped apart, and then you get a change in temperature. So we are really modeling what happens inside of a cold pack. That's our phenomenon. We're modeling that inside of a little styrofoam cup. And my assistants will be conducting this lab, and we'll see how our results come out. I hope they come out great. So this is the cold pack lab. The cold pack lab with ammonium nitrate and water and my 3 tiny assistants. Well, one is not so tiny, one is tiny. one is medium. Okay, so we are going to model a cold pack by using ammonium nitrate as an ionic compound. Now, let me warn you guys. See how you all, don't touch your face. See how you all have your safety gear on? That's because ammonium nitrate is irritating to the skin. I don't even want him to touch it. You two can handle it and just be very careful about it. It's also an explosive. So, we don't want to explode it, all right? But it's not going to explode in this form. It has a coating on it, but it can be used as an explosive. That's one of the things that nitrogen is known for. Like, you guys know Captain Marvel? Captain Marvel? Like nitro. Anyway. All right, well, you probably don't know this Captain Marvel. Anyway, so the first thing we're going to do is measure out the portions. So Ian, could you turn on the balance? Giovanna's going to measure out the portions very carefully. The portions don't need to be exact. Now what are you going to do, Ian? Good. They need to be about how much, Giovanna?
10 grams.
Right, so she's going to add it. Wow, almost there in one scoop. As long as it rounds to 10.0, then it's good.
Just like a few
Maybe
more.
a speck more, maybe even just one little more. It rounds to 10. Oh, you might be able to get it exact if you just
Yeah.
put it. Oh, I would slow down. That's it. That's it. Boom. Okay, good. So that's our first portion. Let's put that aside. And we're putting them into beakers instead of just measuring them on paper this time. So now notice how that one has a slightly different mass, right? Those are the same beakers from the same company, but they have slightly different masses. There's always variations in glassware. Try to avoid that.
Yeah, sorry.
Okay. And then she's going to continue to do that until she has all 4 portions. Now, what are you doing, Lucy?
Oh, I already wrote this.
You wrote the names, and then what are you doing with the water while she's doing that?
I'm gonna put in 50 milliliters.
Ian, you got to help her out. Help her out. Right, so let's do it. Now, some of it you can pour in until you're close to the top.
Oh yeah.
I would pour it in until you're close, and then use the pipette to get the exact amount. When I say exact, I mean within the margins that we can read on the glassware. And Lucy is very familiar with reading a meniscus, right? So where do you read from on that meniscus?
Exactly above, like right above the line.
What do you mean? Like, see how it's a bowl shape?
Like on the line.
The bottom of the bowl, Lucy, has got to be on the line. That's what you do. She's getting it right to 50 milliliters. And Giovanna's figure is at the 3rd portion. The 4th portion. She's already on the 4th portion.
Yeah.
So each portion is going to be the same. And we're going to add them one at a time. This is very similar to what happens in a cold pack. When you break the seal, when you slap the cold pack, the water rushes in. Take out a tiny bit that doesn't quite round to 10.0. That does round to 10.0. That's good. Oh, good.
Oh,
wow. Wow. It's almost like the balance knows what you're going for, right?
Okay.
Okay, well, now we've got our masses. So let's see, we've got our 4 masses. Now we can set that balance over here, Ian. You can set it to the side. That's all we need the balance for.
Okay.
And we are going to, first of all, add the water. Lucy, why don't you pour the water into the styrofoam cup. Now remember, the experiment is taking place inside one styrofoam cup. Now would you describe that as a whole lot of water?
Not really.
that much.
Not really. Does it look like you could pour all of these into there
Yeah.
and have them dissolve?
Yeah.
It does? Okay.
We need to take the temperature.
Okay, oh good. And now we're gonna take the temperature of the water, and this is going to be our first reading. Give it a second to adjust. It's better if it's just off the bottom. So lift it slightly, so it's in the liquid, good. But just off the styrofoam.
25.0 Celsius.
So that's 25.0. What's the unit?
Celsius.
Right, and usually we put that degree sign, that's just a convention. So that's the temperature of just the water. So now we are adding our first portion. This is like a coal pack. Pouring in the first, how much is that?
10 grams
First-
in each of them.
First 10 grams. And, no, just one. And then we're gonna stir it in.
This one?
Yeah, stir it in. Okay, now take out the stir rod. Try not to take any with you. Okay. And then,
I'm just gonna do this just in case.
what's the temperature now?
Oh, it's starting to dissolve a little bit. Okay. 13.7. It keeps going down though.
What you want to get is the lowest temperature. So why don't we stir some more
Okay.
until we get to our lowest temperature.
Yeah, it's dissolving. They're
Yeah,
really
so
small.
stir it really good, really good. You might have to hold it, yeah. Can I get a picture of it?
Yeah. Oh, they're like gone.
Oh, I wish I had gotten it. Okay, now let's get the temperature. Would you say that dissolved quickly?
Yeah. 13.0 Celsius. And
Try to get the lowest temperature it reaches, Javon.
12.8 Celsius.
Is it still changing though? You want to
No,
keep...
not yet.
You sure? Okay.
So it's 12.8 Celsius.
Celsius, yeah.
Yeah. And then if you were writing comments, other observations, you could say it dissolved fast, or you could just write fast there. Not the first, we don't have anything there, but here, fast. In the first one, you could write that it was just water. You could just write water there if you want to.
Okay.
And then now to get this one, and I would have, we're just doing this quickly, but I would write dissolved fast. Okay, so then to get change in temperature, what you're gonna do is you're gonna do the 12.8 degrees Celsius minus 25. So if you subtract a bigger number, then you're gonna get what kind of number? If you subtract a bigger number, what are you gonna get? Something that is what?
What?
Something that is, what is what?
Less.
Negative. Okay, so this is gonna be some kind of negative number, but I'm gonna let students calculate that, okay? Students are gonna calculate that. So now what we're gonna do is the same thing. We're gonna add our next portion. Now notice it says 20, right? But we're only adding 10 more, because there's already 10 in there. So we're just gonna add one more portion that'll get us to 20. Same thing.
Okay.
Pour it in. Stir it up.
Let me make sure I get everything. Got it. And now we do this.
Try to get, can I get here? Is this okay?
Yeah.
You can still stir it. I wanna see the process. Does it look like it's dissolving pretty quickly?
It's a little bit murky.
Okay, Lucy, maybe write that down. What color would you describe that as?
Yellowish?
Okay, write that down, Lucy.
Like tan.
Well, first,
Oh, I have
write.
to
You might want to write those down. That would be here. Okay, and then let's check the temperature. We want to get the lowest temperature. See where it is right now, and see if it's still changing. If it's still dropping, you want to wait.
Okay.
Does it appear to be dropping?
9.2 9.1.
No. If
Oh,
it's
wait.
still
I'll wait
changing,
then.
you want to stir some more. If it's still
Oh, yeah,
changing,
okay, sorry.
you want to get the lowest temperature that this brings it to. So in other words, by adding 20 grams to the 15 milliliters of water, how much temperature change did we get? That's what we're trying to find out here. If it seems to be stabilizing, let's say if it doesn't change for a few seconds, then it's probably stopped. Is it still changing?
Yeah.
So maybe stir it one more time. So notice, depending on when you recorded that temperature, that would affect your data significantly. So what we want to get is if possible is the lowest temperature it reaches. And try to be just off the bottom if possible. Are you?
Yeah.
Okay, good.
We keep.
What was the lowest temperature it reached?
5.2 Celsius.
Yeah, because it got to 5.2 and now look, it's going back up. So then that was the lowest temperature. Lucy, write that down. Okay, so that's after 2 portions. So has it gotten colder?
Yeah.
Are you surprised that we call this the cold pack lab? Does it make sense? Okay, let's add what portion are we on?
3.
The 3rd portion. So after adding this, when she puts that in, what's the total we've put in? What's the total amount we've put in?
We put in, we're at 30.
Right, 30 grams. Okay? And then let's stir it up.
Oh yeah. Okay.
Now you know it's going to take some stirring, so let's just make sure to do, before we even check the temperature,
I'll just stir for like a few seconds.
do a good amount of stirring. Because when you're ripping apart the ammonium nitrate, it doesn't happen instantly. And it's in an ionic compound, it's in like a crystal, so it takes a while to dissolve through the whole crystal. Now there might be a point where it doesn't all dissolve, and if you notice that, then you could write that in your notes over there in other observations. But if it all dissolves, you want to keep track of that. So would you say that it all looks like it dissolved? Or?
I can't even see it. I mean, like, I can't see the bottom of the...
Because, so how would you describe that?
Very murky and brown.
Okay, so very murky. And maybe the color?
It's like tan? I don't know how to...
I mean, you don't... Whatever you would call it.
I mean, I don't know what an exact
Let's get the
color
temperature
would
now.
be.
Let's get
Okay.
the temperature. That's the main thing. And give it time to adjust. And remember, you want the lowest.
Yeah, okay.
So is it still dropping?
Yeah. Oh my gosh.
What's it down to now?
Wait. 0. Never mind, I'm just
No,
gonna
I'm just
wait.
asking you where it is now.
0.7 Celsius. Oh yeah, okay. 0.7 Celsius. Just
And it stopped there?
Yeah.
Okay, good. So let me see what Lucy's writing. And now, by the way, let me just mention something once she writes that. Could you make that 7 a little more clear, baby? That looks almost like a 1. I like to make 7s distinctive. Okay, so then, by the way, we already mentioned that to get this change, it would be the 12.8 minus the 25. And of course, that would be a negative change. Negative changes are when it gets colder. But for this next change here, it would be 5.2 minus the 12.8. You subtract it from the 1 before it. It's final minus initial. So you just subtract it from the 1 before it to get the change. So you can see what the incremental changes are, and whichever one gives us the biggest incremental change is going to be one of the questions on the lab. So mainly we're going to be graphing this data, but we also want to know how much each one changed. So what portion are we on now?
We're on 40 grams.
40 grams. This is our 4th portion, getting us to 40 grams, good unit.
2 of them weren't like exact on 10, like they were just like a little bit.
Yeah, but it rounds to 10.0.
Oh,
Yeah, it's never exact. Sometimes I use the word exact when I mean as good as we can measure it. You're always rounding, even if you don't know it. And in this experiment, getting it plus or minus a few hundredths of a gram is not going to mess us up at all. Okay. So while she's stirring that, let's mention that we're trying to decide if these are endothermic or exothermic reactions. So endothermic is when heat is absorbed by the system. Exothermic is when heat is released by the system. So what's the system? Everything inside the styrofoam cup is our system.
okay.
So if energy is absorbed or released, that'll determine whether it's endothermic or exothermic.
Wait, I can actually see it. That they're like a lot of tiny ones, like a lot on the bottom.
So how would you describe that? Is it dissolving?
Not all of them have dissolved, like from
Okay.
the like the second one, they stayed there.
So maybe write that. Maybe try to stir some more then.
Yeah, okay.
I mean, have you even checked what the temperature is yet?
Not yet. I'm gonna just stir for 2 seconds though. There we go. Okay.
So what should I say for observation?
Not all dissolving.
Oh, it's already in the negatives.
Good. I was hoping you would notice that when it hasn't, because this thermometer. No, I mean this thermometer has a very tiny negative sign and a very tiny decimal. That's one issue with these thermometers. It'd be nice if they made it much more clear, I think.
Okay.
And remember, you want the lowest temperature.
So it's staying at negative 1.8 Celsius.
Was that the lowest one you saw on there?
Yeah.
Okay. And you're saying it's not all dissolving? Why don't we try stirring one more time,
All right, then I'll check it again.
just to make sure it doesn't get any lower. And let's see if that is the lowest temperature, and that will be our last piece of data.
Okay. Ooh.
Let's see. Oh,
Oh, negative 2.0 Celsius.
is it still changing, Giovanna? Look.
Wait, actually, yes. It's gonna wait for a second.
If it stays there for like several seconds, it's probably done.
Negative 2.1 Celsius.
Okay, so Lucy, what was the temperature?
Negative 2.1.
Negative. Write it very clearly. And what's the unit?
Celsius.
Okay, so then what we're going to do is we're going to take that. Remember, that's a negative number, so be careful when you subtract the number before it. That's negative 2.1 minus 0.7 to get the change here. But what we're actually graphing on here, what we're going to graph are the temperatures themselves. So these numbers are going to be plotted here. Our highest temperature was 25, so we got to go a little higher than 25 there. Our lowest temperature was negative 2.1. So that means 0 won't be at the bottom. 0 has to be either this one or this one. So remember, 0 doesn't always go at the bottom. If you have to go negative, so it'll probably be 0 we'll put somewhere around here. 25 or 30 will be somewhere up here. Graph an even scale. And then across the bottom, we've got our portions. This would be with 0. In the middle, that would be with 20. And at the end, that would be with 40. And then here would be 10 grams. So basically every 2 lines. This would be 0, 10 grams, 20 grams, 30 grams, 40 grams. And then we'll see what our graph is. Okay, if the temperature just keeps getting colder at the same rate, like this, then it's equally effective no matter how much you add. But if the temperature change is slower and then faster, well then it's better to add more. If the temperature change is faster and then slower, if the slope of it changes, then that means it's more effective to add less. So we'll see how the graph comes out. So the graph for this lab is very important. So now we're going to check the conductivity. Could you hand him the conductivity indicator? Make sure it's on. Ian knows how to do this. And then here's the well plate. Giovanna, here. So you're going to pour, now that we've got our data, take out the styrofoam cup and pour just a bit of it into that large well. Try not to spill much if you can.
Yeah, okay.
And then Ian's going to check its conductivity. And turn the light toward me, Ian, so we can see if it lights. Okay. And he's going to stick it in. So, would you say that lights up?
Yeah, it's bright red.
Is the green lighting up?
A tiny bit.
It's visible, definitely.
If the green lights up, remember, at all, that means it's an excellent conductor. So would you say this is an excellent conductor?
Yeah.
Do you know why it is? Because these are ionic compounds and they are supposed to be. So we also checked its conductivity, which is something you need for the lab report. Okay, so we got all our data. Thank you guys for the teamwork. Thanks Ian for handling the balances and the conductivity. Thank Giovanna for all your careful measurements and pouring it in. Lucy for being our recorder. Thanks a lot, you guys. Thanks a lot. Bye-bye.